This is Pre-Calculus Section 1.2 Notes, Day 2, Part 2. We left off on example 7. We'd like to add together the square root of 98 plus the square root of 200, but we can't because if we want to add or subtract radicals, we have to have the same radicand. But maybe we can break these apart so that we will have the same radicand. Well, if I'm dealing with square roots, I'm going to be thinking perfect squares. And the perfect square, the biggest perfect square that goes into 98 is 49 2 times. So I'm going to rewrite the square root of 98 as the square root of 49 times the square root of 2. And then 200, the biggest perfect square that goes into 200 is 100. So I'm going to rewrite that as the square root of 100 times the square root of 2. Well, now I can simplify these. Square root of 49 is 7. So that's 7 square roots of 2. And the square root of 100 is 10. So that's 10 square roots of 2. Now I have like radicals, so I can add these together. 7 square roots of 2 plus 10 square roots of 2 gives me an answer of 17 square roots of 2. The next one's a little trickier because I'm not dealing with square roots, I'm dealing with fifth roots, but that's okay. I'm going to do the same thing. I just have to think about perfect fifths. If I've got the fifth root of 64 and I've got the fifth root of 2, I know I can't do anything with the fifth root of 2, so I must be able to simplify the fifth root of 64. So I think about perfect fifths, and 32 is a perfect fifth, and that goes into 64 twice. So I'm going to break apart that fifth root of 64. So I've still got that 7 in the front, and then I'm going to have the fifth root of 32 times the fifth root of 2, because 32 times 2 gives me back that 64. And then I've still got minus 8 fifth roots of 2. Well, now I can simplify the fifth root of 32. That's just whole number 2. And since 7 was being multiplied times the fifth root of 32, now 7 is being multiplied times 2. 7 times 2 gives me 14. So I have 14 fifth roots of 2 minus 8 fifth roots of 2. So now that I have like radicals, I can go ahead and do the subtraction, and that's going to leave me with 6 fifth roots of 2 for my final answer. The last examples deal with rationalizing the denominator. Remember, one of our rules is we can never leave a radical in the denominator. So our goal here is going to be to create a perfect number in the denominator. This will eliminate the radical that we have downstairs. Now, depending on the problem, we're going to, do it based on what we see that we have to try to eliminate. So in example number 1, we've got a cube root or a square root of 3 on top. That's fine, but we've got a square root of 5 on the bottom. So the question is, if I want to make a perfect number in the denominator, how can I make the square root of 5 a perfect number? Well, I need to make 5 into a perfect square. Well, the easiest way to do that is to multiply it by the same radical. You've been doing this since Algebra 1. So we're just going to multiply top and bottom by square root of 5 over square root of 5. In the numerator, we have got the same index, right? We've got the same type of root. They're both square roots, so we can multiply those together. Square root of 3 times square root of 5 gives me square root of 15. In my denominator, square root of 5 times square root of 5 gives me square root of 25, which I know is a whole number 5. So final answer is square root of 15 over 5. I successfully rationalized my denominator. Number 2 here is a little trickier because I'm dealing with a fifth root. But remember, our goal is to create a perfect number in the denominator, right? So if that's what we're trying to do here, if we've got the fifth root of y squared, then we want to turn y squared into y to the fifth so that we have the fifth root of y to the fifth. So the question is, how many more y's, fifth root of y's, do we need to multiply by? We've already got 2. If we want 5 total, then we need to multiply top and bottom by the fifth root of y cubed. Okay, so that's going to give me in the top 7 fifth roots of y cubed. Nothing can be done about that. That's going to stay that way. But then on the bottom, I'm going to have the fifth root of y to the fifth power, which again, same root, same power, cancels. So I end up with 7 fifth roots of y cubed upstairs over y downstairs. And that's going to be my final answer.